This is the second part of a problem we did earlier. We did 6a, now we're doing 6b. It says, from the following three integrals, choose one whose convergence or divergence can be proved by comparison to the integral in part A and give proof. Well, part A, we proved that 1 to infinity of 1 over x dx diverges. So of these three integrals, we have to pick one that lies above it. So this is 1 over x, and we need to find the integral that lies above 1 over x. Because if this area from 1 to infinity is infinite because that integral diverges, adding a little bit more to it is also going to be divergent. If it was underneath, we wouldn't know if that little bit of space that was taken away by the new integral would make it finite. Everything's very fine lined right here. So the easiest one to eliminate right now is this one here in the middle. Because I'm going to take x, which is the same as my denominator here, and I'm going to add something that's always going to be positive. So if I have something x and I add something positive to it, and I take the reciprocal, this is always going to be a value that's going to be less than or equal to whatever 1 over x is, because the denominator here is bigger than the denominator here. So I can eliminate that guy. This one here, we have this trig function, and it's not squared, but I do know that sine x falls between the interval of -1 to 1. Right? Remember the sine function. There's no functions or no values of sine that fall outside of that interval. So now I want to think about how this compares. I have 1 over x plus sine x. And I can think about, okay, if sine is at its greatest value, I'm going to have 1 over x plus 1. And if sine is at its smallest value, I'm going to have 1 over x minus 1. Now, the thing that you want to look for are these outside guys right here. Neither one of them look like my integral that I'm working with. So we're just going to eliminate that because it's not similar enough to what we want to compare to. You're trying to compare to this integrand, and neither one of these two are those integrands. And that's pretty much the only way we can think about this, because sine of x changes so many ways, so that this integral is going to be boxed between here, and neither one of these look like my integrand here. So that leaves this one here. Now we're going to do something similar here as we did here. And let's think about this. So I have the idea that sine x lies between -1 and 1. So that means 2 plus sine x lies between, that's -1, sorry, -1 plus 2 and 1 plus 2. Now, for x greater than or equal to 1, which is what we're working with right here, I know that 1 over x is going to be less than or equal to 2 plus sine x over x, which is going to be less than or equal to 3 over x. And that's only true because x is greater than or equal to 1. Other than that, we wouldn't know what the inequalities would do. But positive 1 greater than 1 x values will not change these inequalities. So you can see this guy over here is 3 over x, which doesn't matter. But you can see here that I can compare 2 plus sine x to 1 over x here. And it's the appropriate one, 1 over x less than or equal to 2 plus sine x. So if this is true, I can say the integral from 1 to infinity of 1 over x dx is less than or equal to the integral from 1 to infinity of 2 plus sine x dx. Oh, sorry, 2 plus sine x dx. 2 plus sine x over x dx. So that's true. And since we know the integral from 1 to infinity of 1 over x dx diverges, we know that the original integrand, 1 to infinity of 2 plus sine x over x, diverges as well. So this isn't the same as the ones that we typically did over and over in class because sine is a varying periodic function. So this idea of comparing it to things from extremes works because this is the lower bound of sine, lower bound of sine, lower bound, lower bound. So, and this matches what we learned in the previous problem, diverges. So there's our proof.